So in this video, I just want to look at one more example of a loop program and use our brute force algorithm to find constraints and show what's wrong with the system of constraints that we find, or not necessarily what's wrong, but what's inefficient about the system of constraints that we find on the initiation interval. So let's just consider a simple function that's really similar to the one we've been working with for the last few videos. So it's just going to be a loop where we set ai to be a function of a previous element of a. But in this case, instead of setting ai to be ai minus 2 plus 1, we're going to set ai to be ai divided by 2 plus 1, and we're going to iterate with I from 2 to 8. So we're going to have iterations for 2, 3, 4, 5, 6, and 7. So, well, let's just execute this loop in our head and see what the dependencies are. So the memory access pattern here is going to be, well, at the first iteration of the loop, I is going to be equal to 2. So we're going to write to the address 2 of a, and we're going to read to 2 divided by 1, which is 1. Then in iteration 2, I is going to be 3, so we're going to read from 3 divided by 2, which is 1, rounding down, and we're going to write to 3. Then we're going to read from 2 and write to 4, then we're going to read from 2 again and write it to 5, and then we're going to read from 3 and write to 6, 3 and write to 7, and then we'll be done, because when we increment I again, we'll get 8, and I is no longer less than 8. So that's the memory access pattern. Now let's apply our dumb checking every iteration algorithm to find all the read-write memory dependencies. Well, and also just remember, in general, as in the past loop, the value of I at iteration k is k plus 1. So in the first iteration, I is 2. In the sixth iteration, I is 7. So here's a brute force algorithm. For k equals 1 to 6, because there's going to be 6 iterations of this loop from 2 to 8 exclusive. And then for j in k to 6, so for all of the iterations at or after a k, if a of, again, this is k plus 1 equal to k plus 1 divided by 2 plus 1, so basically if a of, the value of I at the kth iteration writes the location read by the jth instance of this instruction, then add the constraint that the end of the instruction has got to be less than or equal to the start of the instruction plus I times j minus k. And this is just an adaptation of our brute force algorithm from the last video to this new loop nest, which has a slightly different instruction. So we can simplify this down and get basically, because here we're writing to k plus 1, and here we're reading from j plus 1 divided by 2, we can reduce this to basically when k plus 1 is equal to j plus 1 divided by 2, we're going to add a constraint on the initiation interval that the end of the instruction is going to be less than or equal to start time of the instruction in the basic block plus I times j minus k. So just running this in our heads, what are we going to get? Well, first let's just simplify down a little bit. We can distribute or multiply this 2, and get 2 times k plus 2 is equal to j plus 1. And then we can simplify that down to basically when 2 times k plus 1 equals j, we'll add a constraint on the initiation interval. And so just executing this symbolically, well, when k is 1, we're going to have, and j is 3, we've got 1 times 2 plus 1 is 2 plus 1, which is 3. And then when k is 2, we've got 2 times 2 plus 1 is 5. So when j equals 5, we'll have and k is 2, we'll have a constraint. Then when k equals 3, we'll have, well, 3 times 2, which plus 1 is 7. So when j is 7, we'll add a constraint. But actually the bound on j is from k to 6, because this loop only has 6 iterations. So we're only going to have 2 constraints. And when we add these constraints, what we're going to get is end of the instruction has got to be less than or equal to the start of the instruction plus the initiation interval times 3 minus 1, and then same thing plus the initiation interval times 5 minus 2, which is going to reduce to the same thing, end of instructions less than or equal to start of instruction plus the initiation interval times 2, and end of the instructions less than or equal to the start of the instruction plus I times 3. So what's wrong with this system of constraints that we generated from our brute force algorithm? And what's wrong with it is that it's inefficient. So if you remember, the initiation interval is a positive number. It's always greater than or equal to 1. So if the start time of the instruction, so that means that the start time of the instruction plus the initiation interval times 2 is less than or equal to itself, the start time of the instruction plus I times 2, plus the initiation interval, right? We can't reduce this value by adding a positive number to it. Which means that the start of the instruction plus I times 2 is less than or equal to the start of the instruction plus I times 3. In fact, actually, we could change this to be strict because it's greater than or equal to 1, not greater than or equal to 0. So it must be the case that if the end time of the instruction in the basic block schedule is less than or equal to the start time of the instruction plus 2 times the initiation interval, then by definition it's got to be true that the end time of the instruction is less than or equal to the start time of the instruction plus 3 times the initiation interval, right? Because 3 times the initiation interval is strictly larger than 2 times the initiation interval, because the initiation interval is positive. So the first constraint implies the second constraint, and actually, this isn't a coincidence. It's a general fact about any system of constraints that we find with this algorithm. So actually, if you look at any system of constraints, if you generate a bunch of constraints for any two instructions, call them instruction 0 and instruction 1, and they're of this form, right, that the end of instruction 0 is less than or equal to the start of instruction 1 plus I times the difference between j and k, where there's a bunch of different j's and k's for the different pairs of iterations that could depend on one another. If it's the case that for every q, jq is greater than or equal to kq, so j0 is greater than or equal to k0, j1 is greater than or equal to k1, and so on, then, and this is true, right, because if you go back, our algorithm always searches with j at least k, right? So it's always the case that jq will be greater than or equal to kq, right? The j value will always be greater than or equal to the k by construction. So we can actually just search this list of constraints for the pair jq and kq which have the smallest difference. And this difference is always going to be non-negative because jq is greater than or equal to kq, right? It's at least 0. But if we search this list for the smallest jq minus kq, then what we'll find is that that constraint with the smallest difference between j and k will actually imply all of the other constraints. And so that smallest difference is called the read after write dependence distance between instruction 0 and instruction 1. And dependence distances are a really crucial concept for a lot of loop optimization. It's not just in hardware, but also things you see in software like vectorization. And they're really an abstraction that describes how close together could interfering or dependent iterations of a loop be. And there's different dependence distances for different kinds of dependences, and there's different dependences for each distances for each pair of instructions. And we're going to talk a lot more about dependence distances, but basically what you need to know is it's the smallest distance between loop iterations where two instructions could have some interference through memory. So it's a conservative estimate of how close together two instructions could be in the loop iteration that could depend on one another. And we're going to talk a lot more about it, so don't worry if I'm not being totally clear or if this doesn't make total sense. But what you do need to understand for now is that basically in this giant list of constraints that we generate by brute force, actually there's one of these constraints with the smallest jq minus kq that will imply all of the others because the initiation interval is a positive number. So next time we're going to talk more about dependence distances, and we're going to come up with a more general and more efficient way to compute dependence distances that actually will use integer linear programming and will work for a reasonable range of real loop access, memory access expressions that we'll see in real important applications. So stay tuned for that.